We present DOME, a user-in-the-loop method for exploring optimal designs of environments which account for how people use a space. At each iteration, DOME provides a set of diverse designs which satisfy user-defined constraints and optimality criteria. The user selects a design and iteratively works towards a solution that both fits their needs and is predictive of movement in the resultant spatial forms. DOME does not replace, but empowers designers by deeply integrating with existing pipelines to help them explore the complex solution space of designs for human utilization. Here we present an overview of the DOME method. Starting with an initial environment design, DOME computes different spatial metrics to quantify visibility, accessibility, and organization of the space. While any metrics may be computed over the environment, these measures are predictive of spatial utilization and human movement. The designer specifies one or more focal points in the environment with respect to which different spatial measures are computed. For example, the designer may wish to maximize the visibility of a key location with respect to the exits in a room. The designer specifies permissible alterations to their current design as bounds on the degree to which different environment elements may be transformed. The designer is given the tools to freely parameterize the environment. This affords both subjectivity and strict adherence to constraints such as structural or subjective criteria the designer must accommodate. DOME efficiently searches through the space of permissible environment configurations to identify diverse yet optimal candidates using a novel, hierarchical, multi-objective optimization algorithm. The designer reviews each of the candidate designs, which are then used as the basis for subsequent alterations through a tightly coupled design and optimization process. Using DOME, designers can leverage computation to account for hard-to-interpret factors such as accessibility and visibility of an environment with respect to its human occupants. The diversity set members are provided to users in terms of fitness metrics and are visualized with their modified layouts and heat maps. The designer may browse these and make an informed decision on whether any of the candidates suit their needs. We demonstrate the efficacy of DOME on several examples. We use DOME to minimize the complexity of a maze to produce an altered design with direct paths between the entrance and exit. DOME is then used to maximize the complexity of the simple environment, which produces a design similar in complexity to the original maze with circuitous paths to the exit. We comparatively evaluate both the simple and complex environment in a 3D walkthrough experiment. A virtual walkthrough demonstrates the difference in complexity more clearly. The inversely optimized maze is confusing and requires more searching. The optimized maze has very straightforward paths with visible goals. A user takes significantly longer to navigate the complex maze while finding the exit with ease in the simple case. We use DOME to alter the design of an art gallery in an effort to improve the relative visibility and accessibility of its exhibits and organization of the overall space. We compare the original and optimized design through a first-person walkthrough experiment. The resulting design produces larger exhibit areas with greater visibility from the main corridor, making them easier to spot and capture the attention of patrons. The optimized gallery has greater exhibit visibility at all points along the main corridor. Areas with high congestion are reorganized to have greater space, while the back portion of the gallery with many paths is simplified. The overall space is significantly easier to explore for patrons.